Preorder. Okay, so this is regarding using DAG to check the Preorder. So on the last lecture, using the queue and stack. Okay, this is regarding for the using DAG. So it's pretty straightforward. What do we do here? Push back all the each of the characters, right? Or number, whatever. And then we compare. On both sides compare. Have a while loop goes out, both sides compare. If it's a non-match, we just return false. Okay? All right. Any questions for this topic, for DAG, Q, DAG? Okay, you guys need to review the code. Okay, make sure you understand. We have the question regarding for this, okay, on midterm. Okay, tree. Let's starting with the tree. Tree is a very important topic because it's very, very well used, also in the machine learning. So it'll be very important data structures, fundamental data structures. Okay. What's a tree here, though? It's tree is a hierarchical data structure made up of a node connected by the edge. So tree made by what? Node. So what's a node? We've been using a lot for node, right? For link sensing based by the node. Node we have what? Data and also the pointer. Okay, at least one pointer, right? That's a node. For example, this is a tree. That's the simplest tree we can see. Okay, so how many nodes? What's a node? Sorry, what's a node? A, B, C is a node. What's the edge? So the way connect between the node, we can call the edge. So from A to B, that's one edge. A to C is also one edge. So what's the relationship between node and edge? I mean the number. If you know the number of a node, how many edge? Yeah, minus one, right? So the one differences. Okay? So tree is not linear. Tree is not linear. Before we see the linear, all the linear like linked list, queue, stack, it's all linear structure. But start from tree is not linear. So that's why they can solve the much more complex problem. Why we use a tree? We discuss some because there's some scenarios we need a tree, the structure to solve, right? Hierarchical data. There are many hierarchical data in our daily life, right? Like a company organization, it's a hierarchy, right? So CEO and then multiple people report CEO, multiple manager report CEO, and employee report to multiple employee report to each of manager. So that's a hierarchical data, okay? So this also provide a very efficiency, improve the very efficiency on search, insert, delay operation. We can check the queue and stack, some of their deletion or insert. Some are pro and cons, so we can say just a single linked list, right? But tree, they can improve a lot this step. Okay, compiler. They're using the tree structure as well. They call the abstract syntax type. I think on Summon 1, you guys using what? Prefixed, right? Postfixed, right? So what they do here, for the machine able to read, they don't want to hand off the bracket, right? They want to find out what kind of the priority calculation, right? So they build it as a tree for each of operation for that on compiler. Machine learning. What tree being used? I think you guys were working on machine learning. Not deep learning yet. Not deep neural network. Just machine learning. No? Okay. Classification, regression, right? They use a decision tree. Okay. Like a random forest. This kind of model. All right. I think in the future, if you guys go to work, more or less you touch this kind of topic. Okay. Random forest. How to classify your decision tree in the random forest model. For example, just one model. Okay, and also some other examples. They need very heavily using on the tree. Okay. Okay, some terminology regarding for tree. First, root. It's the topmost node, we call the root. Parent, a node with child nodes. Child, a node descending from a parent. Sibling, the node that share the same parent. Leaf, a node with no children. Internal node, a node with at least one child. Depth, a number of the edges from the root to the node. Height, number of the edges in the longest path from the node to itself. Okay, to the leaf, sorry, to the leaf. Subtree, what's a subtree? A tree formed from a node and its descendant. Like this tree, right? What's a root? A is root, right? Good. Okay, give the example of a parent. B is, okay, because they have children, right? B is a parent. A also a parent, right? C is a parent. D also what? Child. D is a child, but also the parent, right? Okay, so what about E? E is not, right? They don't have a child. Okay, so F not. G is a, well, is a parent as well. I is a parent. Okay? Child. B is a child related to A. C is a child related to A, right? D, E is a child related to B. F, G is a child related to C. Okay? Same principle. H is a child of the D. I is a child of G. J is a child of I. Okay? Sibling. For example, B is a child. C we can trigger what? Also sibling. But we don't call that the one on the real when we work on the code. We also call the children or something. But anyway, you guys know that. Okay? Leaves. What's the leaves? H and J. Okay? Internal node. At least one child. Beside this and this and this and this is all the internal node. Okay? Depth. Depth we're going to use a lot for depth. Okay? So there's a lot of argument we define the depth. Number of edges from root to the node. For example, for B, what depth would be? 1, right? What depth of edge? 1, 2, 3, right? Okay. What depth of J? 1, 2, 3, 4. What's the height? 4. Height is based on the entire tree, longest path, right? So it's 4. Okay. Subtree can make a lot of subtree, right? This is a subtree, this is a subtree, this is a subtree, and this is a subtree. Okay. Yeah. Okay. Types of tree. There's a lot of types of tree. Today we focus on the general tree, very general tree. What's a general tree? Each node can have what? Any number of children. That's a general tree. Okay? For example, this is a general tree, right? So A have what? 3 children. Okay? Let me have more. There's a lot have more. Okay? Okay, general tree is what? Most flexible format of the tree. So it gives there's not a lot of restriction, not like a binary tree or some other thing. They have the strict regarding for number of children, okay, but they don't have it. They can model a real world of the hierarchy, right? Example, we had what? File system. We build a what? On the computer, we build a hierarchy for the folder, subfolder, right, and then file. This is kind of the using what? General tree to establish. Okay. Organization chart, we just mentioned about company chart. Okay. All right. Each node keep a list of pointer to a children. So if we want to build a structure of the node for general tree, what do we do? When you have on the node, when you have what? Have a value. We need what? And then what do we need? We need the many children. How to represent the many children? Array of pointer, yeah, array pointer, or we can use what? A vector, a list of the pointer. Okay. Dynamic array, right? To list as many as the pointer to point to the child nodes, okay? Okay, traversal of a general tree. They define the two types. First, we call the preorder traversal. Okay, so the visitor node first and then its children from the left to right. Second, called postorder traversal. They visit all children first and then to visit a node. Okay, so let's start for the preorder traversal. So visit the node first and then his children, right? From left to right. So let's break down this rule, right? So it means what? First, visit what? Current node first, and then recursively visit each of children from left to right. What's the principle they follow? From top down and left to right. Okay, it's a preorder traversal. Let's have an example here. Okay, let's work together. If you have the preorder traversal, how is it going to work? What's the first node they visit? Be 1, right? Good. And then, yeah, from what? Left to right, right? And then from 2, their children, right? And then 3, and then 5, because it's from top and down. From after 3, they go to their children. 5 and 6 from left to right principle, right? And then 5, 6 finish. Go where? Yeah, 5, 6. Okay, 6. And then last one is 4. Okay, so in this way to work through. Okay. So if you want to write a code, if you plan to write a code for preorder traversal, what's the first impression you can think about? If you want to solve in the computer, right? In the program, we use what? Recursor. The first impression we think, because it's a similar behavior, right? We can use a recursor. Okay, on recursor, solve by recursor. What's a recursor? How can we solve a recursor?
You check if there's any children, and then
And
you call
children.
the first element, and then
Yeah.
when it returns, you call it the second element.
Okay.
Third, and then
That's
you
good.
go
Yeah.
to
Yeah. Okay. So if you are very clear the each of step, you can code in that your way, right? But if you're not quite clear, summarize the mathematical model, right, to build the recursion relation, which we learned before, right? Okay. Let's do some analysis regarding for recursion relation in the tree. What base case? Yeah, no pointer, right? Until the end, right? And then they jump out, right? So the node pointer and no pointer, so will be what? Will be do nothing, return. Okay? Otherwise, we can figure out the time to visit n node equal to what? Equal to a time visit the node, for example, this one. We don't worry about their sub children, okay, and children and the grandchildren, whatever. We just worry about this and their children. And then the recursor will handle the rest, okay? We worry about this one and their children, okay? The time they go with 1, okay? And then 2, and then 3 and 4. That's what it does, right? Okay? So, mean what? Root node plus k children. That's how it works, right? If you write in the formula, right? For entire time equal to 1. 1 is the time cost to visitor itself, and then to visit their children, right? Their children are going to recursively to process to call themselves, right? The function itself. Okay, make sense? Yeah. Okay. So this is what sum up I from 1 to k. Okay, for also plus for all their children being the time being visited. For example, this one, if you assume this is 1, okay? With node 1, it's time cost 1. How much cost 2? Still 1, right? Because single node. How much cost 3? Do you recursively do this? 1, 2, 3, right? This is the 1. This is 1. Raised to 4 is 1. Okay? Make sense? That's how the equation comes from. Okay? Once we know this relation, we can write the code. Pretty straightforward. Okay. First, what? Base node, base case. Base case, right? First step is base case. This is the base case, right? Once pass the pointer or pass the node, right? If this is none, we do nothing, return. Otherwise, this visits the current node, and then we do what? For loop for their children. On their children, doing the recursor. Okay, that's it. Okay, good. Makes sense, right? What's the complexity? What's the complexity? Log n, yeah, log n, good though. Based on how many nodes, right? Each node will have to visit once. That's all about. Okay. Now, big O of n. That's what worst scenario. What's the best scenario?
There's only one node.
1. You can just 1 can visit all the nodes.
No,
Yeah.
there's only one node. There's
Okay, only one node. But if there's a node there, if there's a tree there, fixed tree there, is there any way to improve? Yeah, no. It's you have to visit the node once. Okay, so the best scenario for one tree is still n. Okay, that's a tight bound. Okay. So we can see the difference, right? To transversal, right? So we can give the n linear relationship. Right? Okay, good though. As a DP, there's no duplicate redundancy process. That's why it's not DP. You won't improve the time complexity if you change to iterator. What's a DP? No. Okay, let's go. Let's do in the iterator. Okay, this is iterator. Let's quick go through the code. We're using stack. Okay, to do the iterator. Okay, same tree. Okay, using stack. If the node point to the non-pointer, which is return, do nothing. Okay. Otherwise, we have the stack. We push the root. All right. Push the root will be push this one, right? Push the first node 1, right? And then we go where? This case the stack is not empty, right? We go inside. Okay. So what do you do here? The node on the top. What's the top so far? Yeah, only 1, so it's 1, right? And then they pump up. Okay? So they're going to print what? Print the data. Okay, print the node of data. What next here though? This is a for loop for I equal to node children size -1 and I greater than 0 minus I. So in this case, node children size equal to what? For this node, the children, they have what? Three, right? Have 3 children. Only says later, okay? 3 children, right? 3 children -1 is 2, right? From which way? From which way? From this one to this one, right? From right to left on the stack. Okay? First the input was the I equal to 2, right? So the index this one. Okay? And then to 3, and then to 2. In order to make this work, you need to build the what? Build the tree from left to right. That's usually to build a tree from left to right. You send the what? Send the order on the vector. You send the order, right? From 2, 3, and 4, and then you have to use this to reverse order of that into stack. Okay. Any question for this part? No. Okay. You put into stack, and then come back. Is it empty? It's not empty. Of course, not empty, right? The tree node equal to the what? Top. What's the top? 2 is the top, right? Okay. Now they pump up, and just C out, print the value of 2. Okay, for 2, they have children or not? They don't have children. Okay, so we do nothing. And then keep loop, right? Keep loop. What's the top now? 3, right? Okay, 3 is gone. Oh, I'll give you answer already. Go here, right? Print here. And for 3, they have the children. Now they push their children. Reverse order will be 6 and 5 into the stack. Okay, now keep loop. It's now none. What they do here? They send the node for the top 5 and pump up. Okay, 5 is gone. Print here, and then next 5. Is that 5 have children? No, right? It's a leave, right? Don't have children. And then they keep going, right? What's the top now? 6, right? And 6 pump up. Okay, they don't have children for 6 as well. Okay, now they keep while loop, and they're still not empty, right? What's the top? 4. Okay, 4 into pump up and print the value. 4 don't have children either, right? So in this case, the while loop is it's empty. And jump out. Okay, now post-order traversal. Post-order, visit all the children first and then the node. Oh, by the way, do you have any question regarding for preorder? For code, make sense? Okay, good. All right, okay. Okay, post-order traversal. Visit all the children first and then to the node. Let's convert into the sort of the programming methodology way to describe. This is what? Recursively transverse all the children from left to right and then process the node. Okay? From what? Left to right, from bottom to up. Kind of, up and down, they're different. Okay? Okay, let's, same example, let's go within the post order. Okay? Well, which first? Children first, right? From left to right? Okay, 2, right? Good. And then?
5, and then 6 and 3.
What? 5. Children first, right? 5. And then? 6. And then? 3. Because finish the children and then go with the parent, right?
Yeah.
Go with the current node. And then?
4 and 1.
4. And then last one is what? 1. Okay. The root will be last. Okay. For what? For post-order traversal. Traversal, sorry. All right. Okay. Doing the same thing. Able to resolve what? By what? Recursion, right? Recursion. So by recursion, what are the recursion relation? We define the base case. What the base case?
No children.
Same as what on the pure order. Well, okay, so this null pointer will be do nothing. And then time to visit in the end node, what are going to conclude? Children first and then himself. Based on k children and then plus their root node. Same equation, different order. Before the 1, preorder 1 is a first and then do this. But now children first and then do the what? Do the node self. So we go with the base case and then what? Do the children first. Do the children, it's same code. And then what? Do the node. Okay, that's it. But it gives a big difference, even though it looks like the code very similar. So the behavior is different. Well, what's the complexity?
Same.
Same, all same. Okay, tight bound. All right. Okay, you study by yourself. Okay, the code here, you study by yourself. Please study, okay? Study, okay? All right, okay. Why do we need this tool, traversal? have a pre-order and post-order, right? So the order first from node to children, and then from children to node. The different two use cases. The pre-order is what? They process parents before their children. Post-order, what? They process all the children before their parents. Family tree, company chart, right? We have the what? From the top to bottom, okay? CEO to manager and to employee. What others? You found we already make example, right? If on the computer, if you want to make an archive, organize all the archive. May not be on computer, in any kind of archive solution. You need to using this kind of the methodology, right? Pre-order traversal, right? Folder, subfolder, and then file, right? Parent first, and then the children, okay? Also fill the form, right? So you can personal information, and then you can fill your name, address, and then personal information is a big sheets of form, right? And then they have the children. Children means each of the your specific information there. Okay. When you design this type of the structures, you think about it, it's a big potential to have the pre-order traversal on this tree. Okay. Decision tree, AI. Decision tree is also the pre-order traversal from top to bottom. Post-order traversal, an example. Let's go backward. Delay. If you want to delay the directory on your PC, what do they do? Okay, you build the directory, right, based on the pre-order. If you want to delay, what the computer do? The post-order, right? Delete the file, and then first on the file, and then folder, and then corresponding the file and the folder, right? Also, postfix to solve the mathematical expression. It's on Simon 1 there. Okay, so they're doing this type of tree. Okay, so they from here and then have the operation, and then have the doing here and doing the operation. Okay. Again, compiling source code. So compare the evaluate inner function and then express first and then wrap up to the outer layer by the AST, abstract syntax tree. We're using on compiler.